Hello, this is Ben Leonard, and this is the third lecture of my introduction to tribology. Slide lecture is Making It Rain, a light overview of tribology, or of lubrication. The first lecture was an overview of tribology as a whole. The second lecture looked at wear. This lecture looks at lubrication. In the fourth and final lecture, we'll look at friction. I'm going to begin with the introduction and objectives. Then we will look at some background information. Just to give everyone a little bit of terminology before we get into the meat of the presentation and get us up to speed on some related and I think at least somewhat interesting topics. Then we'll talk about the lubrication regimes, and we will cover the lubricant families, and we will finish by wrapping up. The objectives of this lecture is that when we are done, you will know and understand the Stribeck Curve, understand the lubrication regimes, and know the families of lubricants. So to begin with, what is lubrication? Lubrication is the process or technique employed to reduce friction between and wear of one or both surfaces in proximity and moving relative to each other by interposing a substance called a lubricant between them. So what does that all boil down to? We've got two surfaces that are touching or are very close. The surfaces are moving relative to one another. Friction is resisting that motion. Wear can be taking place. What you're trying to do is get a lift or get some separation between the two bodies. So now into some background information. We're going to talk about the different types or shapes of contact. Moving from left to right, we've got a conformal contact. Then we have a non-conformal Hertzian line contact. Then we have a non-conformal Hertzian point contact. So in a conformal contact, the surfaces conform to one another. In a non-conformal contact, the surfaces do not conform to one another. What that means is that non-conformal contacts have a relatively small contact area and conformal and high pressure, whereas conformal contacts have a relatively large area and low pressure. So when you have two flat surfaces touching, have the apparent area of contact will be the entire surface. When you look at it at a disparity level, the area of contact is different, but we're looking at it from a large scale. The apparent area of contact. And then when you get to a Hertzian line contact, it's very narrow. It's a long, narrow contact, much smaller, just where that cylinder touches the flat surface. And in a non-conformal contact, you've got, for instance, a ball on a flat, and you've just got a point. So this is sometimes called a point contact. And you can see pressure going down and area going up as we move from right to left. Also, roughness. Intuitively, we know that roughness plays a role with lubrication. You calculate, if you say, okay, we've got a lubrication film of, say, 2 microns. How well is that going to work? Well, it depends on how rough the surface is. if you've got a very coarsely ground, very coarse surface finish, say you're just some cast iron straight out of the mold, it's not really anything. But if you've got a ball bearing with those highly polished surfaces, 2 microns is a lot. So how what we use to kind of identify or take this into account is a film thickness ratio. This is often signified by lambda, the Greek letter lambda, and it equals the minimum film thickness divided by the equivalent surface roughness. The equivalent surface roughness comes when you convert the roughness of both contacting surfaces into an equivalent single surface. This is calculated by squaring the roughness of both surfaces, adding them together, and then taking the square root. So the film thickness ratio really gives the ratio of lubricant film to surface roughness. All right. Some of you may have already heard about the Stribeck curve, and you can see that lots of places. You see it most of the time in a figure somewhat like this, where there's no numbers on the axes, and it's just kind of a curve which is kind of drawn in. It's a characteristic shape. The surface roughness, the friction starts high on the left side, then it starts decreasing and it starts increasing again. This comes because you're moving between different lubrication regimes, and this, as you look at the film thickness here, the blue line, the reason for the shape of this friction curve becomes more clear. So on the y-axis here we have coefficient of friction, and on the x-axis, every time you see it, it could be something slightly different, but different parameters you can have are velocity, the inverse of pressure, viscosity, and the inverse of roughness. Sometimes you'll have several of these multiplied together. Sometimes you'll have a parameter that's calculated that's based on these values. So as we start off on the left, you have boundary lubrication. Here the surfaces are actually touching. They are separated by a molecular film which covers their surface, or by some solid additives, but with some minor materials interposing themselves, the asperities are touching each other. Then you've got mixed lubrication. So in mixed lubrication, you'll have regions of the contact which are in boundary lubrication, and other places where you've got a lubricant film separating the surfaces. And here you can see the H, the film thickness, is starting to increase, whereas it was roughly 0 or about the level of the surface roughness beforehand. And then you get into hot, and during mixed lubrication, as more of the surface becomes separated with lubricant, the friction goes down. And when the surfaces finally come out of contact with each other, the friction will start increasing again, and now you just have the surfaces are not touching directly. They're entirely separated by the lubricant film, and what we see is that as you move further to the right, it takes more effort, more force to shear that, or stress to shear that lubricant film separating the surface, and that is what's causing the friction to start rising again. we aren't seeing a reduction in friction from the fewer asperity contacts, which is what was happening in mixed lubrication, because there's no more asperity contacts to be removed. So we'll discuss each lubrication regime in a little bit more detail. For boundary lubrication, the lambda value, the ratio of film thickness to roughness, is generally less than 1. Film thickness typically 1 to 50 nanometers. You can see some schematics illustrating what's going on here. You've got surfaces and you've got a layer, a boundary layer, called attached to them, and that boundary layer is interposing itself between the two surfaces. Next we have mixed lubrication. The film thickness ratio, or lambda, is typically between 1 and 5, and film thickness is at a general range of 0.25 to 2.5 microns. Here we also have some schematics on the left-hand side, and this is, you see that you have a lubricant in place between the surface, and you got roughness, and in some places that roughness is causing the surfaces to touch, whereas in other places the surfaces are being separated. So you've got intermittent contact, and you're not too far away from actually getting the surfaces completely apart in some cases. So you can see on the right-hand side, we've got an example of a film thickness and pressure from a Hertzian point contact. Film thickness, you can see it's very thin, and you've got some areas in there where the surfaces are actually touching, but a lot of the surface is separated. When you look at the pressure has the same, with a perfectly smooth surface, the pressure profile will look like a dome, although it may be stretched out in terms of the, based on the aspect ratio of the contact, the relative size of the length and the width of it. And you see a general dome-like shape, but it's a lot of spikes. And those spikes are the areas where the pressure, where you have asperity contacts, and the actual lubricated areas are not supporting nearly as much of the load. Next, we're moving into elastohydrodynamic lubrication. Here, the lambda ratio is between 3 and 10, and the film thickness is typically 0.1 to 1 micron. If you remember, we talked about conformal and non-conformal contacts earlier in this presentation. So elastohydrodynamic lubrication takes place with non-conformal contacts, like a Hertzian point or Hertzian line contacts. This would be ball bearings, roller bearings, gears, piston, cylinder liner, and why it's called elastohydrodynamic is the elastic deformation at the contact is significant relative to the film thickness. Before this regime was actually discovered, people could not figure out why these contacts did not fail, because they were calculating the lubricant films as less than a micron thick. You can see some examples. Here you've got Hertzian contact, the schematic of a Hertzian contact on the upper right corner. You've got a schematic of the an EHL contact in the upper center. You can see that there's deformation of the surface. You can see that lubricant wedge, the lubricant being drawn into the surface. You can see the rolling of the ball. On the right, you've got the film thickness and pressure profile. The pressure profile looks very similar to a Hertzian contact, except you've got a pressure spike at the end of the contact, and the pressure goes out in front of the contact. The size of those two differences will change depending on the conditions of the contact. And when you look inside the contact, you've got generally flat parallel surfaces, and then at the end it dips down. That's correlated to the same spot where you've got the pressure spike, and that is that happens in order that the continuity equation, conservation of mass, is maintained. The bottom two, so the top left, that shows the pressure and film thickness for a Hertzian line contact. So we're saying this goes infinitely long into the page, or roughly infinitely. And in the bottom, you've got it for a point contact. So on the left is the film thickness, and on the right is the pressure profile. So you can see that there's a lot of similarities. If you take the center line of the contact, the rolling direction of motion here is, you'd say it's going from the back right of the screen to the forward left. So if you take the center line of the contact in the rolling direction, it will look like that figure in the upper left. But you can see here that low film thickness area extends around three sides of the contact. The area where the film thickness doesn't drop is the inlet, and same, that pressure spike kind of curves around the side. So this is classical EHL pressure and film thickness shapes. Next, we are going to discuss hydrodynamic lubrication. Here, you notice it's the same as the previous regime, except for there's no elasto at the beginning. This means that the elastic, gives us a clue about the elastic deformation. It's not important here, and that's the primary difference between these two slides. The film thickness ratio is generally between 5 and 100, and the film thickness is between 1 and 100 microns. You see the film thickness is generally thicker here than with elastohydrodynamic lubrication. And that is because with the larger surface, it's harder to keep them separated over the entire thing. When you look at a Stribeck curve with the lubrication regimes drawn in, they oftentimes show elastohydrodynamic as being a region in between mixed and hydrodynamic lubrication, but in general they happen with different shaped contacts. So common examples of the hydrodynamic lubrication are journal bearing. You can see that in the center top schematic of that, and then the pressure from a journal bearing, calculated pressure profiles on the right. You can also see on the upper left a typical surface here. You've got the full film lubrication separating the surface, and on the bottom left you've got a parallel step slider bearing. Because there's no elastic deformation, the lubrication problem for these is much easier to calculate. So you see a lot. I use Fundamentals of Fluid Film Lubrication by Hamrock quite a bit, and you've got also, he's compiled a lot of figures that show the performance characteristics for different hydrodynamically lubricated contacts. You see that if you look at the dates that those papers are calculated, they were calculated fairly early. So these solutions have been around for a while, and it's even though the calculations aren't as difficult, you can oftentimes just find those charts and look up the data. And then the final, we've got hydrostatic lubrication. Here, the word itself again will give us a clue. Hydro, like hydrodynamic, you want to have full separation of the surfaces here. And static, it's not moving, as opposed to hydrodynamic. So in a hydrostatic contact, the lubricant is going to be pumped in, and that external pressure is going to keep the surfaces apart. So this is frequently used when you've got insufficient velocity. So an example could be when you've got intermittent motion, or for during startup and shutdown, moving very slow, or you're stationary. Now let's review the lubrication regimes again. For the boundary lubrication regime, we're saying that the lambda value is less than 1, film thickness 1 to 50 nanometers, and if we have to summarize it in a phrase, we're going to say the surfaces are in contact. Then we've got the mixed or partial lubrication regime, lambda value between 1 and 3, film thickness 0.25 to 2.5 microns, and summarize this by saying part of the surface has full film lubrication, the rest of it is in solid contact. Then we move to Elastohydrodynamic Lubrication. EHD and EHL are the two abbreviations for it. Lambda value 3 to 5, film thickness ratio 0.1 to 1, or film thickness ratio 3 to 5, film thickness 0.1 to 1 micron. Again, these are all kind of rules of thumb, not hard values. Our comments: full separation, significant elastic deformation, although you do oftentimes you're going to have some asperity contact, especially at first. Then you go to hydrodynamic lubrication, lambda ratio 3 to 10, film thickness 1 to 100 microns, and we've got full separation. Hydrostatic, you can think like hydrodynamic, full separation, but no action, no motion is required because we're pumping in the lubricant. Next, we're going to go into cover the different families of lubricants. So we're going to move, I guess, in terms of decreasing viscosity. So you start off with the solid lubricant. This is something like PTFE, molybdenum disulfide, graphite. It's often applied as a coating on the surface, so there can be particles. And then next we move into semi-solid lubrication. This is grease. Here it can flow, but it tends to stay in motion. It's kind of intermediate. It's got an oil with something in it that thickens it. And then you've got a liquid lubrication. There you've got a fluid, and it oftentimes will have a few particles in it, although it's not thickening it in the way semi-solid is thickened. And finally, you've got gas lubrication. So solid lubrication, you are going to be in boundary lubrication. It can be applied as a coating, or it can be put in a solvent and sprayed on, and the solvent evaporates. Typically the form is, if you look at it at a fine scale, you've got layered platelets making up the solid lubricant, and those platelets are able to slide relative to each other. That absorbs the difference in velocity between the surfaces and reduces the stress on the surfaces. And this is also a component of other lubricant families. You put these solid lubricants in other. So what you want to do here is you want these solid lubricants to be kind of sliding, the different layers to be sliding, and you have a kind of a light film of them separating the surfaces. But sometimes they will peel up from the surface, kind of delaminate, debond, push out of the way. And then you've got the direct surfaces coming into contact, and that is not what we want. So with a semi-solid lubricant, this is again a grease. You've got a liquid plus a thickener, and then some additives as well. It can be in any lubrication regime from boundary to hydrodynamic. What we see is that at low speeds, the thickener tends to enter contact, whereas at high speeds, it does not, and it's just the oil that does the lubrication. A semi-solid lubricant is good because it has a lot of the benefits of a liquid lubricant, but it's able to stay in place, and that especially helps in startup or with intermittent motion. And then we've got liquid lubrication. Again, can be in any lubrication regime, although it doesn't work as well for boundary. The additives in it can be very helpful for boundary. It can carry away contaminants. It also provides cooling. And the viscosity is the most important parameter. Typically, it's going to be recirculating in an application. So the most famous of these is like motor oil or engine oil. But we use hydrocarbon oils mostly today, but in the past, animal and plant oils were used, and they are still used today. And then you've got gas lubrication. This is This will always be in the hydrodynamic lubrication regime. Works with light loads and high speeds. It works over a wide temperature range, but it has poor stability. Air's viscosity is about 1,000 times less than oil, so that gives you an idea for the type of problem we have. So there can be all sorts of bearings. You've got journal bearings. You can have radial bearings, thrust bearings. One of the interesting things I've seen is that with some of the most advanced ships, they're actually having gas lubrication on them, putting a layer of bubbles, gas, in between the hull of the surface of the hull and the ocean. So some key points to take away from this presentation. The Stribeck curve presents the relationship between friction and the variables of pressure, velocity, and viscosity in lubricated contact. Also, roughness. Lubrication regimes describe the type of surface interaction in a contact. The main lubrication regimes are boundary, mixed, and hydrodynamic lubrication. Hydrodynamic lubrication is similar to elastohydrodynamic lubrication and hydrostatic lubrication. And then the four types of lubricants are gas, liquid, semi-solid, and solid lubricants. Each lubricant works with different lubrication regimes. So at this point, if we were in real life, you could ask some questions, but since we're not, you can maybe check out my website or do an internet search, and you can find a lot of interesting stuff about tribology and lubrication. Or you can take a course at a local college. Thanks for your time, and the final topic coming up will be friction.